how fluids move in different way, we can come to know by this knowing the equation of continuity or equation of motion. An article that is equation of motion contains the equation from simple flow to complex flow. Fluid are everywhere and it is necessary to understand the behavior of fluid, and it also help us to design the pumps and pipes. That is different types of derivative. First we come to know that how there are different types of derivative. That is, first, partial time derivative, that is del C by del T. We are taking this partial time derivative with respect of x, y and z. That is the directions, that is the coordinates, that is the x, y and z, that are the directions. This del C by del T, that is C is the rate of change of C with respect to time, keeping all variables constant. C can be anything, that is concentration of chemical in a solution, temperature at specific point or displacement of a point. We can come to know that is total time derivative. Total time derivative is equals to del C by del T. It represents the overall rate of change of that function with respect to time, that is x, y and z. That is del x by del T into del C by del x at y, z and t with respect, it is changing with respect to t. Then we can say that dy by dt into del C by del y, that is z, x and t with respect to z, x and t. dz by dt into del C by del z into, that is x, y and t, changing with respect to x, y and t. Substantial time derivative, del C by dt is equals to
substantial time derivative,
that is dc by dt is equals to vx into del C by del x plus vy del C by del y plus vz del C by del z plus vy del C by del y plus vz del C by del z. As we have discussed earlier, that is del C by del t, that is a partial time derivative, and C can be replaced by any variable, that is temperature at specific point, concentration. Equation. Now we come to discuss the equation of continuity for continuous flow. That is concept of continuous flow. It is very important, as I have earlier discussed, that it is the phenomena that we can, it is help to design the pumps and pipes. Concept of continuous flow. For a fluid flow to be continuous, we require that velocity v is in x, y and z direction, and it is changing with respect to t. We can discuss the concept of continuous flow through this equation of continuity. For a fluid flow to be continuous, we require the velocity v, that is x, y, z and t, to be finite, and it is a continuous function of x, y, z and t. D, that is time, and x, y, z are the Cartesian coordinates, that is x, y and z. Consequences of continuous flow. No segment of fluid can be consequences of continuous flow. No segment of fluid can be joined or broken apart. The interface between two materials' volumes always exists. Can be joined or broken apart. The interference between two materials' volume always exists. The interference between two materials' volumes always exist. This we discuss the consequences of continuous flow in the equation of continuity and concept of continuous flow. Thus, we can come to know across the fluid how the fluid is moving through a circular pipe, through a circular cross section. Then we can apply the formula for rate of equation of continuity, that is rate of increase of mass is equals to rate of mass in minus rate of mass out. Here we do not include the terms that is generation and consumption, as here is no fluid is generating or consuming. It is simply the fluid is coming out and the fluid is coming in and fluid is going out. That is rate of mass of fluid that is coming in and rate of mass of fluid that is going out. And we can comparing it with respect to time, that how much mass come in and how much mass goes out. We consider the coordinate system, as we have discussed earlier, that we can observe the change with respect to x, y, z and with respect to time. So here we can draw the figure like it is in x direction, it is in y and z direction. We consider the element that is cube. Here we are considering the cube, that is fluid is flowing through this cube, that is 3 dimensional. Here we are considering the 3 dimensional coordinates, that is x, y and z. We can come to know how the fluid is changing with respect to time. That is, we can apply here the equation of continuity, that is rate of increase of mass is equals to rate of mass in minus rate of mass out. So we can name this equation, that is we can name these coordinates, that is x, y, z, and that is the element that is the length of cube, that is del x, length of del y, length of cube, that is del y in y direction. Similarly, length of cube in z direction, that is del z. Then we can differentiate, then we can consider the differential element, that is del x, del y and del z. We can rate of mass out in the cube, that is we can represent it that density into velocity. Density has a dimension kg per meter cube, while velocity has its dimension meter per second. We can multiply these both so that we can get our rate of mass, that is kg per second, into area, that is meter square, that is we can get the whole dimension, we can get that is kg per second. Here total rate of increase of mass, that is mass with respect to time, that is del rho upon del t into volume, that is kg per meter cube into volume as a dimension of meter cube, that is kg per meter or kg per second, if we multiply the terms together. Here rho Vx into cross sectional area, that is del y into del z. Here rho Vx into cross sectional area del y into del z, that is at x plus delta x, into del y into del z, that is the cross sectional area. Here rate of mass in minus rate of mass out. If we consider for y and z direction, that is velocity, we for y and z direction, velocity, that is fluid is moving in x direction, that is velocity is in x direction. So mass flux we can write as density into velocity, that is kg per meter square second. That is flow area, that is cross sectional area, as we are considering in y and z direction. So del y into del z, as we are considering the lengths, del y means length, area of cube, that is L square, and del y into del z, that is mass per unit time. Then we can write it as rho density into velocity into del y into del z. We can combine the above terms, that we can get the mass per unit time. That is rho is the density, velocity is Vx is the velocity in x direction, and as I earlier mentioned, del y into del z is the final cross sectional area. Here the fluid can move in any smaller cross sectional area. Fluid is flowing in every second and it depends upon its density and its velocity. This leads to the concept of divergence that we will discuss later on. Now we here apply the equation of continuity, that is rate of increase of mass is equals to rate of mass in minus rate of mass out. that is rate of increase of mass that I have already discussed, that is del x into del y into del z into d rho by dt is equals to cross sectional area at x direction, that we are considering the x direction, as we are considering the fluid is moving in x direction for y and z direction, that is cross sectional area into rho into vx minus mass of rate of mass out, that is rho into vx, that is x plus del x into del z into del y, for y the rho into vy minus rho into vy at y plus del x into del y, that is rho into vz minus rho into vz into z plus del z. We are considering here for particular equation, that is equation of continuity for particular coordinate system, that is x, y and z, that is rate of fluid coming in x direction, so rho vx, and rate of fluid going in x plus del x, that is rate of fluid coming in at rho into vx, and rate of fluid going out, that is rho into vx at x plus del x. Similarly for y plus del y, and similarly for z plus del z. Here we can simplify the above equation by dividing it del x, by dividing the whole term with del x, del y and del z. Thus we can simplify, that is, and we can write that d rho by dt is equals to minus of del by del x into rho vx plus del by del y into rho vy plus del by del z into rho vz. And thus here the concept of del operator comes, telling us that how the fluid is expanding, that is negative divergence mean water is coming like a point, while zero divergence means flow is balanced, comes in and comes out. Flow is balanced, that is flow can come in and flow can go out. For incompressible flow, density is constant, and for gases density can change with respect to temperature and pressure. So here del is the del operator that I have mentioned just now, net of rate of mass addition per unit volume by convection. Here del is the divergence. Here where del into rho into v is the divergence of rho into velocity. Divergence of rho into velocity. Rho into velocity, that is del. We can also expand it as, that is del by del x plus del by del y plus del by del z. Thus we can differentiate it with respect to density and velocity. We can put the del operator in the above equations. So we are discussing, that is del rho by del t plus vx into del rho by del x plus vy into del rho by del y. Actually here we are differentiating it with respect to density and velocity, as I mentioned above earlier, that is we can applying here mathematical rules, that is we are differentiating two terms with respect to one term, that is density, keeping velocity constant, and differentiating velocity with respect to keeping density as a constant. So as you are see that we are getting our final results as del rho by del t plus vx into del rho by del x plus vy into del rho by del y del z plus rho into del vx by del x plus del vy by del y plus del vz by del z is equals to 0. Now as I mentioned earlier, that is d by dt is a substantial time derivative, and del is the divergence, that is del operator, and that determines how the fluid is expanding or converging, that is negative divergence, positive divergence and zero divergence. Similarly we can prove it for different Cartesian coordinate systems, that is for cylindrical coordinate system and spherical coordinate systems. As I said, similarly we can derive the above equations for Cartesian coordinate system, that is for cylindrical coordinate system, and for spherical coordinate system. Here I did not derive for every cylindrical coordinate system and spherical coordinate system. I am directly representing the formulas, that is for cylindrical Cartesian coordinate system, that is x, y, z, that is we have already derived in the above mentioned pages, that is del rho by del t plus del by del x into rho vx plus del by del y into rho vy plus del by del z into rho vz is equals to 0. Then similarly we can prove for cylindrical coordinates, that is r, theta and z. In place of x and y we are considering here it is as r and theta, as it is for cylindrical coordinates. That means that are cylindrical coordinates. So for cylindrical coordinate our formula is del rho by del t plus 1 upon r into del by del r into rho r into vr plus 1 upon r into del by del theta into rho v theta plus del by del z into rho vz is equals to 0. For spherical coordinates, that is r, theta and phi, here in place of x, y, z, for spherical coordinates we consider the terms, that is r, theta and phi. So we are representing the formula, that is del rho by del t plus 1 upon r square into del by del r into rho r square into vr plus 1 upon r into sin theta into del by del theta into rho v theta into sin theta. Actually here velocity is in theta direction, and we can neglect the terms according to our problem, and we can solve the with help of these equations according to our problem. Plus 1 upon r into sin theta into del by del phi into rho v phi. Now we are considering the equation of motion. In equation of motion, what causes the fluid to speed up the change down? Considering the fluid moving with a thin pipe, we consider here the pressure forces acting on a pipe, friction, and we can also study the velocity profile, that is how velocity is varying in center to at the surface. We need a generalized approach of equation of motion that is mentioned in this video. The content tell us that the molecular momentum and convective momentum. Convective momentum is the flow being transported on the bulk motion of fluid, while the momentum being carried out along the flow, that is the stress within the fluid, that is momentum flux at molecular level. It comes all these terms, that is convective momentum flux and molecular momentum flux, that is comes in the equation of motion. Equation of motion basically, as I said, that is deals with the convective momentum and molecular momentum. Momentum means flux into area. So here we are dealing with velocity is in x direction. So we are considering the flux that is changing with respect to x, y and z direction, that is phi xx at x minus phi xx at x plus del x into area. As I mentioned, it is the momentum, that is area into flux. Similarly for y direction, phi xx. Similarly for y direction, that is phi yx minus phi yx at y plus del y plus phi zx at z minus phi zx at z plus del z. That is total force acting on the element. We can draw here element, and is equals to rho into g into del x del y del z. That is del x del y del z is the volume of the element. Now we are drawing the element in x, z and y direction. We are mentioning it as a x, z and y. Here we are now drawing the cube, considering the three-dimensional system, that is x, y and z. Here we are considering the x, y and z, and now we consider the flux that is in xx direction, flux that is zx direction, that is flux in zx direction plus flux out in zx direction, flux in xx direction, while flux going in xx direction, that is place of flux in x direction, that is x plus del x. Here we are mentioning the coordinates at each corners of the cube, that is x plus del x in comma y plus del y comma z plus del z. That is I already mentioned, that is plus zs, that is z plus del z going out, that is plus zs z into zx, and z that is coming in. Basically this is fluid coming in and coming out, but now instead of equation of continuity, here we are applying the equation of motion, and here we come across the flux into cross sectional area, as this is the equation of motion, and we are considering here the momentum. So that's why we are considering here flux into area. So now we can generalize the equation, that is equation of motion, that is rate of increase of momentum is equals to rate of increase of momentum is equals to rate of momentum in minus rate of momentum out plus external force on the fluid. As I already mentioned that here we are not neglecting any of the forces, that is frictional force or pressure force. Here we are considering the forces, that is pressure force and pressure force, gravitational force and frictional force. According to fluid, how it behaves in the pipe and how it changes, from that we can neglect the term of forces, that is frictional force or pressure force. But here, as the fluid moving from top to bottom in a pipe, we have to consider the pressure, as pressure is changing as the fluid is moving from top to bottom. At top the pressure is high, while at bottom the pressure is low. So we have written the equation of motion in terms of momentum. Then we can, for simplifying the terms that are coming in next, we can divide it by del x, del y, del z, as we have done for equation of continuity. To simplify the terms, here also we can do the same, that is we can divide del x, del y and del z. Okay, and taking the del x, del y, del z approaches to 0, we can similarly simplify the equation as we have done it in earlier case, that is the case of equation of continuity. That is del rho by del t into rho vx is equals to del by del x into phi xs, del by del y into phi yx plus del by del z into phi zx plus rho gx. Here rho gx is the force, external force on the fluid, that is acting on the fluid. As I mentioned earlier, we are considering the forces that are acting on the fluid. Now it is in x direction, we can write it for y direction, and we can also write it for z direction. That is velocity is in x, velocity is in y, and velocity is in z. So similarly we can write the term, that is del by del t into rho vy is equals to minus of del by del x into phi xy, that is with respect to y we are considering now, plus del by del y into phi yy plus del by del z phi zy plus rho g into y direction, that is the force in y direction. Now for z, del by del t into rho vz minus of del by del x into phi xz, that is plus is in in z direction, plus del by del y into phi flux phi yz plus del by del z into phi zz plus rho gz, that is force acting in z direction, that is force we are considering with respect to z direction. In play here, the difference is that in place of velocity, flux term is introduced, that is we have already seen in earlier case, that is in equation of motion we are considering there the velocity, and in equation of motion we are considering it as a momentum, that is in picture flux is also there. So here also del operator comes, but instead of, as I said, instead of velocity flux is there, plus also some additional forces are there, that is density into gravity, that is rho into gi. I is the specific coordinates, that is data, that is nothing but x, y, z. So we can again simplify the terms. We can again simplify the terms and we can write flux as I mentioned here in equation of motion. We can consider here two fluxes, that is convective momentum flux and molecular momentum flux. We can simplify the flux, that is rho. We can simplify the flux, that is rho Vv plus pressure into thickness plus tau. Pressure into thickness plus tau. Here rho Vv is the convective momentum flux. As I mentioned that a convective momentum flux is the flow of momentum being transported on the bulk motion of fluid, while the molecular momentum flux is being carried along the flow, that is stress within the fluid, that is at the molecular level. That's all come in general equation of motion. And here we also introduce the new term, that is tau. Tau represent the stress that is the internal stress, and it is related to viscosity, that how different layers or fluid are flowing on each other. It also represent the resistance. It also represent the resistance of the fluid. These constants also represent the equation of motion with various different Cartesian coordinate systems. Here del by del T into rho V is equals to rate of increase of momentum per unit volume, and del is the del operator. Del into rho Vv is equals to rate of momentum. It is addition by convective flux, as I mentioned earlier, is a convective per unit volume. Rate of momentum, and the whole term, that is minus del P minus del dot tau, that is represent rate of momentum by addition of transport by molecular transport per unit volume. That is because of molecular momentum flux, that is minus del P minus del into tau. And rho G, as I mentioned earlier, that is external force on the fluid per unit volume. Rho into G, that is rho represent the density, while G represent the acceleration of gravity. Here we are not considering the pressure forces and or frictional forces, as viscosity is not mentioned in these cases, so we are not considering the frictional forces. We are only considering the forces that is due to gravity, that is rho into G. G is the acceleration due to gravity. Thus we can simplify the terms, and we can put the value of phi in place of phi we introduce in the above system. So the equations are quite complex, but we can simplify it, and we can neglect the terms according to our assumptions, and according to our diagram we can neglect some of the terms. As I have mentioned earlier, that is we discussed the rate of increase of momentum per unit volume is equals to rate of momentum addition by convective per unit volume plus rate of momentum by addition of transport by molecular transport per unit volume plus external forces on fluid per unit volume. So we can simplify the further equations, that is del by del T into rho Vx, that is in x direction. Here we are considering now in x direction, is equals to minus of del by del x into flux in xx plus del by del y into flux in yx plus del by del z into flux in zx plus rho gx, that is the external force on fluid in x direction. That is the x equation of motion, that is phi is equals to rho Vv plus P into del plus tau. As I mentioned earlier, that is rho Vv is the convective momentum flux and P del plus tau is the molecular momentum flux. So now we are introducing the term that is we have discussed earlier, that is dc by dt, that is the substantial time derivative. We can write it as del c by del t plus vx into del c by del x plus vy into del c by del y plus vz into del c by del z. Now we can, as it is the mathematical term, so we are introducing some mathematical terms, that is del is equals to del x, del by del x plus, that is the gradient, that is del by del x plus del by del y plus del by del z is equals to minus of del p upon del x, that is the, as I mentioned earlier, that is the pressure, frictional and gravitational forces are acting on the fluid. So pressure is in x, the pressure is changing with respect to x direction, that is we can mention that del p by del x minus of rho del by del x into tau xx plus del by del y tau yx plus del by del z into tau is in z changing in x direction plus rho gx, that is pressure, that is force due to gravity, that is rho into dv by dt is equals to minus of del p minus of del into tau plus rho into g. Now we can also further simplify the above terms, that is del by del t into rho vx minus of del by del x into flux in xx plus del by del y into flux in yx plus del by del z into flux in zx plus rho gx. Here flux is equals to rho vv plus p into del plus tau. Here we can write phi xx, that is rho vxx means vx square, but we are not writing it as a square, we are writing density into velocity in x direction into velocity is in x direction plus p into thickness in xx direction, that is 1, and thickness for xy and yx, that is 0. So in place of del 1 come, so del rho into vxx plus p plus tau, rate of change of momentum, that is tau represent the actually p plus tau xx whole term represent the molecular momentum flux, as I have already mentioned, that is thickness is equals to 1. So phi yx is equals to rho vy into vx plus tau yx, as I have mentioned that thickness will be 0, that is flux is in yx, and also thickness is 0 for flux that is in zx direction, and thickness is equals to 1 where we are considering the flux, that is for flux xx, that is tau that is in yx plus for phi zx, that is rho vz into vx, that is plus tau that is in zx. Now we are further simplifying the terms, and we can put the value of flux in place of flux, that is del by del t into rho vx is equals to minus of del by del x into rho vxx plus p in plus tau into xx.